All right, how did everybody do on the worksheet? Everybody get it done? Okay. Mm-hmm. Okay, so turn to the second problem. You got the step-by-step. Okay, turn to the second. Okay, for the calculate, so step one, so let's just go over that real quick. Heat absorbed by the calorimeter. When we see the term heat, we know that we need the units joules, right, or kilojoules. Okay, so if we go back and we see that our calorimeter constant is 24.0, okay, and then we know our change of T was 1.88. Okay, so on step one, you should have gotten about 45.12 or 1 joules. Okay, did everybody get that? Okay. Step two says you need the grams. Well, if you are given milliliters, then you have to use density to convert to grams, right? So you take 100 milliliters, because that was the total of the two. So if you look at the problem, you've got 50 of copper sulfate and 50 sodium hydroxide. Okay, so now go like that, and you get 102 gram solution. So now we have the mass. Okay. Damien was asking about step three. We want Q, heat absorbed by the solution. Okay, so you have to really pay attention to the wording here. So we know now that Q equals MC change of T. So I set you up in the problem to solve for mass, right? Okay, so we've got 102. Okay, C is given 1.18 or 4.18 or 4.184 joules per gram per degree C. Okay, change of T was 1.88. Okay, so when you do the math, you get about 802 joules. Okay, grams cancel. Degree C cancel, so you're left with joules, which is what you want as your unit. Okay, all you do there is plug into our heat equation. Okay, step four, you need to add the heat absorbed values to solve for the total amount of heat evolved for the reaction. Okay, so we remember we have two components here. When we use calorimetry and we place reactants here, it's copper sulfate and copper 2 sulfate and sodium hydroxide. Okay, they're going to react in the vessel in our calorimeter, and they're going to, in this case, it's exothermic, so they release heat, right? So they're going to release the heat, and the solution's going to absorb the heat, right? So there's that. This is Q solution. Okay, and then what else absorbs the heat that's given off? The calorimeter, and so we have to go back up to step one where we found that value, and now we add 802 and 45.1, and we get about 847. I think I had 45.12, but joules. Everybody with me so far? Stop me now if you are. We're about to move on to something totally different. So, yes. Okay, we're about to do that. Let me pull this back up. I hadn't even taken attendance yet. We can do that too. Okay, so we found Q, which is joules, all right? But if you're asked for delta G, or excuse me, delta G is what we're going to talk about later. Delta H, okay, then you have to have joules per what? Moles. Okay, so now we have to find moles, and we have to find moles of the limiting reactant. Okay, so I'm going to show you in the PowerPoint, we did the kind of the longer way, or kind of showed it. I'm going to show you how I do it to prevent error. Okay, it's a little bit shorter, but you can do this two ways. Okay, so the first thing you have to do is you have to take the volume of each reactant. Okay, so how many milliliters of copper 2 sulfate do you have? Okay, so we have 50 milliliters copper 2 sulfate. All right, if we're given a volume, how do we get to moles of copper 2 sulfate? What do we have to do? Somebody's saying it. Have to multiply by, okay, which is what? 0.400. Be sure you use all your numbers. Okay, we're going to use millimoles because we're in milliliters here. Okay, we multiply times the molarity, right? Molarity is equal to moles per liter or millimoles per milliliter. That's what that is right there, right? Okay. Right. We can stop here. This is the way I do it. So we can multiply these two. We get 20 millimoles copper sulfate. Okay? But then I have to do the same thing for the NaOH. That's my other reactant. Remember, reactants are on the left side. Okay, its molarity is 0.6. So we get 30. Okay. All right, now look at your balanced equation. So flip back and look at your balanced equation that was given to you under the problem. Okay. Our mole-to-mole ratio in the problem is we have for every 1 copper sulfate, we need 2. Okay, so if we look over here at the NaOH, this number needs to be twice as big as this because we need 2 moles for every 1, right? Okay, so is this number twice as big? It's bigger, right? But it's not big enough because it needs to be twice. So it would need to be 40 to be equal, okay, to have what you would call a stoichiometric ratio. So in this case, our NaOH is the limiting reactant. Okay. You can keep going, like in the PowerPoint, and find the moles of, keep going and find moles of a product. Okay, you can do that. The problem is you have to remember that the number you plug in the last step is not the moles of product, it's the moles of your limiting reactant. So this can kind of help you prevent error, okay, if you just do the one step. The ratios are not going to be crazy. They're going to be 1 to 2 or 1 to 3 or, you know, something like that. So you won't really have to do much, but is it double or is it triple? It's not going to be anything crazy. Okay, so now we found millimoles, which we said we need moles. So we know if we move our decimal back 3 places, 0.0300 moles. Okay. So delta H reaction. Delta H, remember it's written both ways. We take our 847 that we found earlier and we divide it by our moles. And we get 28233 joules per mole. Okay, sometimes, and I will specify if I'm being picky or not, but sometimes you will see in your book, other places, that they'll put a negative there, okay? And all that means, you can't have negative heat. All that means is that they're telling you it's an exothermic reaction, okay? Because you release the heat. Okay?
If that had been 1 to 1 and the 30 or 30 was higher than the 20, would that have been the 20 than the 1?
Yep.
If you're not here,
Okay. Tina, Wyatt, Jeremy, say here loud. Michael. Philip, Alex, Breck, Brian Jones, Bradley Keats, Jennifer, Aaron, Damien, Katie, Justice, Martin, Sarmiento, Torres, Hunter, Sion, Reed, Richard, Cole, Michael, Samuel. Usually comes in late. What's today, the 25th? All right. Yep. I'll provide it. Yep. There's Martin. Get him on here. All right, we got to move on here. Let me pull down the screen. A couple more equations. We should have a few minutes at the end to practice some of these. You have a handout on Blackboard that's got quite a few problems to work, so we may get to start these. Okay, so we've already talked about thermochemical equations. So like I said, in Chem 111, you're just looking at the balancing of your reactants and your products. Okay, and now we know that we want to include a value, a heat or a delta H value in the reaction because heat is either lost or absorbed. Okay, so we have to make note of that in our equation. So if we look at the ratios, so we're going to do problems that are very similar to our grams to moles, moles to grams, but they are different because we're looking at thermochemical equations. So we're actually going to be able to find delta H or heat values because now we have a product. That is a product. It is our heat that's lost in this situation because it's on the product side. Okay, so our coefficients. So we would say, we've got pentane up there and oxygen. We've got a 1:8 ratio, pentane to oxygen. We've got a 1:5 with CO2, 1:6. Okay, but we want to look at now our heat value there. Okay, so what we do is this is kind of a thermochemical language. So you have to kind of get used to it. Okay, it's not. It's kind of, even the book's not the greatest about explaining it because we're used to just doing, mole to mole ratios and moving on. Okay, but we consider this whole reaction to be out of 1 mole of reactions. Okay, never heard that before, right? That's not something we've talked about. Okay, so if we went through and we pulled out all of our unit factors, so our ratios, we would say we have 1 mole C5H12 for every 1 mole of reactions for the whole equation. Okay, so you just have to get used to the terminology. We have 8 moles for every 1 mole of reactions. Okay, your 1 mole of reactions, it's never going to be anything but 1. Okay, so when you plug it in here in a few minutes into equations, it's always going to be 1. Okay, so it shouldn't, hopefully, won't confuse you. Okay, so if we think about, we'll keep moving on. So we have 5 moles CO2 out of 1 mole reactions. Okay, that whole 1 mole reactions basically means that we've now got this, energy, this heat value here. Okay, so same thing for this. So we've got 3,523 kilojoules that's lost in an exothermic reaction per what? 1 mole of reactions, exactly. One thing to clear up before we start doing equations. Okay, there are 2 ways to write thermochemical equations. One is how we just had, this is the same reaction as the previous slide. Okay, one was just to include that plus 3,523 in the products, right? Okay, another way is to write out beside it delta H reaction. Okay, what does that little subdot mean? Ready? constant temperature and pressure. Okay. And out beside that to put negative 3,523. Okay, so that negative sign tells you what? It's exo, meaning that value is going to be added in to the product side, right? So just like the previous slide. Okay, and there's our kilojoules. Okay, if delta H was positive, so out beside it had positive 3,523, that would mean that if you wanted to write that out, including the value, that you would include it in the reactant side. Okay, so here's the other way that we can write this. Okay, so I want you to write it out. Okay, there's two ways that are acceptable, so I want you to write it out the other way. Okay, so I want you to take what you know from this and include it into your equation. Pretty easy, but let's make sure. So delta H is negative, which means what? Reaction is. Okay, and so what we would do, simply add it in. Don't put a negative there. You can't have negative anything in an equation. Okay, that negative just tells you that it is XO. Had that number been positive, then we would have added it over to the left side. So now let's use our mole of reactions. Okay. So first off, I want you to read this. Think about what's going on. Look at the equation. Take just a minute to think about it. Try to even think about what you might do to get to the answer here. If you had me for Chem 111, hopefully you know where to start. They usually tell you if you have grams, that's probably a good place to start. Go from grams to moles. Okay, so what are we trying to find?
It says find delta H.
Okay, very good. The obvious, it's in bold. Okay, and when we use our reaction equation, so we've been looking, delta H is joules or kilojoules per mole. But what we're about to do, stoichiometry, that moles is moles of reaction. Okay, so RxN is for reaction. Okay, so first thing, what do you think we should do? Convert. Very good. How about let's take that 2.61 and do something with it. So we've got grams. Okay, this is dimethyl ether. Okay, right there. So CH3O, CH3. Okay. So what do we need to do to get the grams here in the denominator? We gotta.
We need to figure out what CH15
Okay, we need to go over and add up our molar mass, right? Okay, so if we add up 2 carbons, 6 hydrogens, and 1 oxygen, we should get about 46. Okay. If we use the periodic table to add up molar mass, it's always out of 1 mole, right? Okay, that's because our periodic table is based on 1 mole, always, no matter what the compound is. Okay? Okay, if we look at the problem, this is what we're trying to find, right? Kilojoules per mole reaction. Okay, we're given kilojoules, so that's going to plug in right there, isn't it? Okay. Now we're looking for mole reaction. Okay, so moles in the reaction. So here we've gotten to moles of our dimethyl ether. Okay, so the next step to get to moles reaction is we need to do our unit factor that we were talking about earlier. We said that if we had 1 mole dimethyl ether per what? 1 mole reaction, exactly. So we have a 1-to-1 ratio. We have 1 mole. Okay, that's just because in this problem it has an understood 1 out front. Okay. If we were looking at oxygen, that wouldn't be the case, right? We'd have a 3. Okay, and so we have 1 mole reaction. All right, we do the math. We should get about 0.7 moles reaction. And everything cancels up here. So the only difference with it from grams to moles. And then our second step is our ratio of moles of what we started with 1 mole reaction. It's always 1, so that number up here is always going to be 1. Okay, so we have moles and we have kilojoules given to us, right? So we can find delta H, and we can take our 82.5 kilojoules per mole. We get, I believe I can't read my handwriting. I think we need 3 significant digits, so I guess we have to round to this. Can't read my writing here. 1454, but then if you need 3 significant digits, we'll leave it like this. So I will accept. So we got this negative number here. Okay, all the negative means is that it's given off. Okay, so it's not, so either one. Okay, somehow I got 1454. So if you round to 3 significant digits, see you've got 3 sig figs there. So you need 3 in the answer. Okay, well, if you got a 5, then you would round up to 1460. Yeah. Okay, any questions on this? Okay, grams to moles of what you're given, to moles of reaction, and then divide your kilojoules that you're given by the moles. That gives you your delta H. Okay, so we were able to take a mass of a reactant. So we could do this in the lab, right? Get the mass of whatever we're reacting. Okay, it's burned here, so it's a combustion reaction. And we find through calorimetry that we give off 82.5 kilojoules of heat. So from that, we can find the enthalpy, or the delta H, for the reaction. Okay. there's two different types of problems for these types of reactions. Okay, this one we're finding delta H. Okay, the other way that you could be asked this type of problem is to be given delta H, right? And you're looking for how much heat is released. Okay, so this time, here's our delta H. That negative means exothermic, so if you want to add it in over here, you can. Okay, so read through this. Okay, you're still given a mass, so we know that's a good place to start. Okay, so read through this and try to think about what you would do. Okay, it's really just going to be one more step, or not even, actually, the same number of steps. First thing you're going to do, first two steps are going to be exactly like the previous one. So go ahead and try those. Go from grams to moles. Here it's just aluminum, so aluminum, I believe it's 27 is the atomic weight of aluminum. Okay, once you get to moles, you're going to go to moles of reaction. Okay, but this time you don't have a 1-to-1 ratio. Okay, you've got a different ratio there. .0, I believe. Everybody get this far? Okay, so let's think about where we are. What have we found at this point? Moles of reaction. Okay, so if we were to add on a step to this, what do we need to put in the denominator here? What are our units? They got to be mole reaction, right? To add on to this, okay? Okay, what could we plug in here that would match up, give us a mole reaction, and give us, what are we looking for? Looking for heat that's released from the reaction. So what can we plug in here that would leave us with value of kilojoules or joules? No, that's the temperature. Exactly. So we're given delta H for a reason, right? Okay, earlier, the previous problem, we had to find it. Okay, so all we have to do is we know 1 mole reaction, it's always 1, and then we plug in our negative 3.352 kilojoules per mole reaction. There's our units: kilojoules, mole reaction, kilojoules, mole reaction. Mole reaction cancels. We're left with kilojoules as our units, which is what we want for heat, right? Those are our units. Joules are kilojoules. So if we do the math, I think I get about negative 751 kilojoules of heat is released to the surroundings during this oxidation of aluminum. So that's how much heat is given off by the reaction. Okay? So it's just same two steps as earlier. Okay? Like I said, these are going to be asked two different ways. If you are given delta H, it comes in this last step and you plug it in. Okay? If you are asked for delta H, then we do these first two steps, and then we have to be given a heat value. And then we just divide, bless you, okay, by moles. All right, any questions on those? Yes, I have to. Yep. You just got to pay attention and be sure you read it, as heat versus delta H. Okay, here's some terms. So I asked you earlier what that sub naught means. It does mean constant pressure and temperature, but this also means certain values. Okay, and these do not confuse with STP. Okay, from Chem 111, and for us it was chapter 12 where we talked about gases, and standard temperature and pressure was 273 K and 1 atm. Okay, so the pressure is the same for thermochemical equations. It's 1. But the temperature is 298. It's not 273. Okay, so when you see that sub naught or whatever, that's what it's talking about. For gases, like I said, it's 1 atm. And then for aqueous solutions, if it says that it's at a standard, okay, at standard enthalpy, standard states, then it's going to be considered to be 1 molar, okay, 1 molarity. Okay, so when you see this reaction, that just means delta H of the reaction, and that sub naught means that the chemical reaction is at standard pressure and temperature, which for standard is the 1 and the 298. Okay. All right. We're going to sum all this up here in a few minutes, but we still have another term to look at. So we've seen at this point, I'm not going to put everything up here, but we know Q, right? Got it right here. Okay, Q stands for what? What are we looking for when we find Q? What is Q? Heat. Okay. All right, what's delta H? Or delta H reaction, either one. You see it written both ways. Okay. Oh, what does H stand for? Not heat. Remember, this is heat. What'd you say, Jennifer? Okay. This one's heat, so it's not changing heat. What's the H stand for? Starts with an E. Enthalpy. Exactly. Okay. Which does include heat, because it's talking about the heat transferred or the energy transferred in and out of a system. Okay. All right. So we have kilojoules per mole or joules. So a lot of times we use joules, but okay. We know what C is. We know what our delta T is. Okay. We talked about calorimeter constant, so there's other things. But now we're going to look at what we call delta HF. Okay, remember, if you've got that little sub naught, that can be anywhere, so you can have that there. That just means standard pressure and temperature, 298 Kelvin. Okay, now we've got a new one. I call it the heat of formation because it just makes more sense to me to call it that because there's an F right there, and so I think of formation. Okay. Standard molar enthalpy is the other term for it, so it's just something you gotta, remember. But I will, more times than not, if I'm writing it out, the book may be different, but heat of formation is what I call it, okay, because I just think it's easier to remember. Okay, and it's also, remember, enthalpy is the heat transferred into or out of a system for the reaction. But for the heat of formation, okay, we're looking at how much heat does it require to form a product. So that's where that formation comes from. Okay, and we're thinking of 1 mole. Okay, so we want to form 1 mole of a product. Okay, so the standard molar enthalpy or heat of formation is given this symbol that I wrote over there with the F there. So you got to pay attention when you're reading, okay, when you're doing these problems. Okay, the heat of formation for magnesium chloride is 641. So we have that negative there just because it's an exothermic reaction. Okay, these values right here, these are tabulated for you in your book. I meant to send you an email, but it was like 8:45, and I thought, well, it's a little late for that, to send you an email about bringing your book today, okay, because we're going to look at these values. So in the back of your book, in Appendix K, and somebody can borrow mine, okay, if you've got a book or try to get next to somebody that does, try to share. It may be a different page because we've gotten an updated book. It used to be Appendix K. We'll see. There they are now. Okay, it is Appendix K, A27. Yeah, so the page number is different from what it used to be. Well, yeah, there's some in your chapter, too, so it tabulates some of them in your chapter, but I don't know if that's page 500 or not. Yeah. Back of the book looks like this. Okay, I want you to look. So there's all these compounds here. Okay. I want you to look at that first column. Eventually we're going to understand all of these columns, but today we're going to look at the first one. Okay, if you notice, it has delta H formation. And also notice the units are kilojoules per mole. Okay? Is everybody with me or near somebody that has a book? Okay. Okay, so delta H, heats of formation, are for substances, are tabulated for us. So all of these, so we can just use this table. Of course, you're not going to have to memorize this. I will either just give you the heat of formation or I'll give you, whatever this or a table with heats of formation, okay? Notice it's out of kilojoules per mole. It's all out of 1 mole, okay? It's also at those standard molar enthalpies that I was telling you about. So that means that for these values to be true, you have to be at 298 Kelvin and 1 atm. Okay? For elements that are in their most stable form, so look at the first one. So aluminum solid, it's 0, okay? Because that is its most stable form, and the value is 0. So it doesn't take any energy or any kilojoules per mole to form aluminum solid. Same for if you look down, where's bromine? Br2 liquid. I don't know where it is. There we go, yep. Br2 liquid, 0. Okay, that's the most stable form of bromine. Okay, so if we look at, so everybody find HF. All right, so we have to kind of flip over a page and look for the heat of formation of HF. It should be on here somewhere. Yep, you got to look at, that's a good point. You got to look at the, they're not going to have HF. There it is. It's the very bottom of the first page, actually. Okay, it's HF in the gas form. Okay, this is one of the most common mistakes, is to use the wrong state of matter. Okay, be sure when you look there that you use the right state of matter, because for HF gas it's negative 271, but for aqueous it's negative 320. Okay, so don't get them confused there. Okay, so it's negative 271, but this is based on 1 mole, right? So in this problem, or in this equation, we form 2, right? 2 HF. So our total, so our HF here, heat of formation of 1 mole is 271. Okay, but our delta H, we could say, is 2 times, because we have 2 moles. So we just take that number times 2, and we get negative 542, okay, kilojoules. we're going to keep using this, so keep it open. We're going to learn a nice way to use it here in a second. Okay, this is just a quick review. I kind of already did that up here, but just because I know there's quite a few terms you have to try to keep straight in your minds. Okay, Q, heat flow, MC change of T, units, joules, and kilojoules. Our delta H or delta H reaction is the enthalpy change, and it can be in kilojoules per mole reaction or joules per mole. Okay, heat of formation, also known as standard molar enthalpy. Okay, this is how much it takes, basically how much heat does it take or energy does it take to form a product. Okay, so that's what we're looking at. And it has the same units. So these numbers, these heats of formations, are tabulated for us, okay, in our appendix that we have there. And then our units are kilojoules per mole. Okay, so here's some in your book. This is the table. So I already pointed out bromine is 0. Okay, carbon in the graphite form is 0. That's the most stable form. Okay, it's going to be 0. Chlorine, okay, Cl2. We talked about diatomic molecules in Chem 111. Okay, Cl2 wants to be diatomic so that it has a full octet. That's the most stable form there. And chlorine gas is the most stable. Okay, so here you can see the values here. Okay, so you have lots of negative values as well. Okay, so now we're going to use these heats of formation. Okay, you've already learned, okay, how to find delta H reaction, right? Okay, how do we go about doing that? Anybody sum it up for me? And you often forget sometimes what you're actually looking for and what you already know. Okay, if you could do this worksheet, what did you find? What was your final answer in the very back? What were you looking for? Delta H, right? So you found delta H. Okay. This is our calorimetry, right? So you're going to do this today in the lab. You're going to use calorimetry. Okay. You're going to have we actually have a probe that calculates the temperature, measures the temperature. Okay. And you're going to go through, the first thing we had to do was go through a long series, right? That's what I wanted you to summarize. You had to find Q of the solution. You have to know your calorimeter constant. Okay. Then you have to find Q absorbed by everything that surrounds, right? Okay. Once you find that, then what do we have to do? Find moles, right? So you have to look at your reaction, your limiting reactant, find the moles of it, and then we just divide. Okay? So you already know how to find delta H in one way, and that's this way. Okay? We're going to look at another way to find delta H. Okay? And it includes Hess's law. This is called the heats of summations. Okay? It basically states that you could take the delta H for all the steps in a reaction, and you can find the total delta H of the reaction just by summing all the little steps up. Okay, right now we're not concerned with getting from reactants to products. Okay, in your mind, unless you've had, or you just like reading about chemical reactions, or you've had organic. Okay, we've really just said, okay, these reactants react and they form the products. We haven't talked about what goes on in between here. Okay, in reality, it's not just one step. It's not just bonds break, new bonds form, voila, it's there. Okay, it's sometimes can be 20 steps to get from this place to this. Okay, it's not an easy matter, and that's why for chemists it's very challenging. Okay, but right now you just see reactants, you see they react and they form products. Okay, in reality there's a number of steps that go on. So this is saying, this law, Hess's law, is saying it doesn't matter what goes on between here. We can just add up all the heats and get to the final. Okay? So we can just sum them all up, those steps, to get from one place to the products, or reactant to the products. So that's what it's saying. The change, the delta H reaction, is independent of the pathway, okay, I was talking about, okay, that the reaction undergoes. Okay, so here explain this. Okay, in a more useful form, this is what we're about to do. We're going to use delta HF values, okay, and we're going to find delta H of the reaction. Okay, so this right here, you can read through that, but I'm going to try to make it simplified form. What you do is you take the delta H of formation, notice the F. Okay, if it has an F there, where are you going to find those values? In the chart, either in the book or a chart that I give you. Okay, you take those delta HF, you're going to take the summation of the delta HF values for your products, and then you're going to subtract the formation, the summation of the formation values of your reactants. Okay, so first key thing, products minus reactants. Okay, that's what we're doing. You're taking the sum, so you have more than one product a lot of times, right? So you have more than one reactant. So you got to take the sum of those delta H formation values. The last thing is these A right here. A is the coefficient in the reaction. Okay, if you have 3 moles of some product, you got to take 3 times the delta H formation, right? Because the delta H formation in the book is based on how many moles? 1. So if you have more than 1, you got to multiply times that. Okay. So here we go. Now it looks like a lot, but it's really not bad. So if you take, I've just kind of broken it down here. You've got products, the summation, so that's what we're doing. Our product, we have 3 CO2, so we have to take 3 times the delta HF value that's in the book. Okay. We have 4 H2O. Remember, it's products minus reactants. Okay, so we take 4 times the delta HF of H2O in the liquid form. Be sure you do the correct states of matter. Okay, that's the products minus reactants. So we only have 1, so we find the delta HF for propane, C3H8, and then we have 5 of O2. Okay, if it's 0, so oxygen O2, that's its most stable form. So when you look that up, it's going to be 0. So, and it's in the gas form. Okay, so you just cancel that out. Just don't even worry about it. We have it here because we want to think about it, but it's going to be 0. Okay, so you don't even really have to pay attention to it. Okay, then you just use, this is Hess's law, and you just sum it all up. Okay, so if you look in your, so I want everybody to check. I want you to look, I know it seems elementary, but look in your book and make sure that you see where these values come from, that you agree with them. Okay, a lot of times if I don't show this, students will start giving me all these random numbers, okay, and they are looking at the wrong compound or they're looking at the wrong state of matter. Okay, so first thing, look up your CO2. Okay, use your calculators. You should be bringing those every day or every class. Okay, look up your H2O liquid. Okay, propane gas. We know that one's 0. And then be sure that you get the same answer. Okay, the nice thing about this, using Hess's law to predict delta H, is you're using values that are known, but it also sets your sign here. So it tells you whether it's XO or endo once you get done. Okay, so at the end you get a negative, so you know it's XO. Okay, so work it out. I know it's up here, but I want you to go ahead. Be sure you see those values. Be sure, even write it all out if you want to. Okay, punch it in your calculator. Make sure you get the same answer. they getting the same thing? It's probably just a difference, or the value's exactly the same that you found in the book. Okay, sometimes you'll see that 298 there. I don't want to confuse you with that either. That means that that's the temperature. It's just telling you that it's 298, but it's standard. All right, everybody good? All right, so this is Hess's law, summation of product, heats of formation minus heats of formation of reactant. So we can find delta H by calorimetry that we're going to do in lab and go through our whole little scenario like we did on our worksheet last week. You can also find it by using Hess's law. Right? That's what you just did now. Yeah, you'll have, I'll have the known value. It's at the bottom. So I think one of them is negative 11. Of course, it's not going to be very exothermic. We wouldn't want to do that in the lab. It's like only 11 kilojoules or something. But your answer, and they're not going to be perfect, especially our equipment, we don't have exactly what we would prefer to have because it's expensive. But, hopefully you're in the ballpark, at least in the same sign. Hopefully you get, negative if it's exo and positive for endo. Okay, so this next one is really just algebra, okay? So some situations, so especially if you form a new compound, you may know the delta H of the reaction, okay, based upon your experiment that you did in lab. So let's say you did your calorimetry experiment and you found delta H, but you want to know what the heat of formation was. So it's not in your book. Okay, this is an example of, this one is, but it'd be some compound that you didn't know the heat of formation. So all it is algebra. It's the same idea. It's just you're solving for X, which X is your heat of formation that you're looking for. Okay? So if you look here, don't look at the blue right now. Look up here. Here's your reaction. Okay, you've got SH2, oxygen, forms SO2 and water. Your delta H this time is given. Okay, that's not what you're finding. That's what you're given. Okay, what you're looking for is SH2. Okay, the heat of formation of it. Okay, so if you plug in, so if we do our Hess's law, still the same thing. Okay, we know delta H, right? So we plug it in, negative 1124. Okay, because remember delta H equals all this. So you take that negative 1124 that you were given, okay, and then you take products minus reactants. So here you're not going to have to look in your book. So this is a way that I could just give you those values. Okay, so you take 2 times the 296 because you have 2 moles, 2 times the 285 because you have 2. Then you subtract from the products. Well, from the reactants. You subtract the reactants. Okay, oxygen we know is 0, right? And this is our X. This is what we're looking for. We have 2 moles SH2. So we have 2. If you want to put an X there, you can, because that's what we're looking for. Okay, so now I want you from this point solve for X. Okay, it's just algebra, but I want to be sure that you get the same thing. So you should get over here negative 41.2, but then you got to divide by 2, right? Okay, to get isolate your delta HF for SO2 or for X. Okay, so be sure you know how to work the algebra here. Be sure that you get negative 20.6 before we move on. This is just one more way to use Hess's law. you can isolate your variable either way. So some of you may get, you may have pulled this number over here. Remember when you move something, so here, whatever number you get here, gotta subtract it from that side. Okay, so it's just rearranging just algebra using Hess's law. Are there any questions on this? Okay, I suggest, of course, working these out. If you haven't gotten it done now, working them out at home, be sure you get the same answer. Okay, let me see what time it is before we start this. We've got a few minutes. Okay. I'm going to try to simplify this term. This is just our delta E the best I can. Okay. So it goes into a lot of detail in the book and all these roundabout things. But then when you finally get to the end, you pretty much find out that delta E equals delta H for a chemical reaction. So that's why we're going to try to just simplify instead of confuse. And I'm going to tell you what delta E is and then kind of show you why delta E, for most times, ends up being equal to delta H. Okay? So delta E, okay, this H right here, okay, someone said it was heat. It's called enthalpy, right? This is enthalpy. Okay? But it does involve, that's what we're looking at. We're looking at the heat that's being evolved, generated, released, transferred in a chemical reaction. E is different, and then it includes all forms of energy. So delta E is the kinetic, the potential, gravitational, electromagnetic, could go on and on, rotational, the vibrational energy that's in the bonds, and everything. Okay? The first law of thermodynamics states that the change in internal energy is determined by heat flow, Q, plus work. Q we know is heat, right? Heat can go flow in or heat can flow out of the system. Okay? And then W is work. So work is just basically that you can move something with force over some amount of distance. Okay? That's what work is. Okay? But we're going to try to relate work to chemical reactions here in a few minutes about what's actually going on. Okay. So here's our system. Remember, our system is what we've got in our beaker, or it's our, reactants that they're our chemical reaction. Okay. So Q, if Q is greater than 0, so positive Q, okay, this would be an endothermic reaction, right? Because the system would gain heat. Okay. That's what we said an endothermic reaction is, right? The system absorbs heat. Okay. If it's an exothermic reaction, then we have negative Q, right? Because the system released heat. Okay, same idea for work. So if work is done on the system, okay, that means it's giving it, energy or whatever you want to think about. Okay, if it's doing work on the system, then W would be what? You think it'd be positive or negative for the system? Positive, right? So if work's being done on the system, then the system would be positive, right? Okay, if the system is what's doing the work, then work's going to be negative. Exactly. Okay, so that sums this up here. So it's basically the same thing. Okay. So for delta E, we take Q. It could be positive or negative depending on if it's an exo or endothermic reaction. And then we take our W and we add it to it. And work depends on if work is being done on the system or by the system. So if I'm doing the work and I'm the system, then I just lost W, right? Negative W. Okay, so you can also write in delta E like we've been seeing with delta H. Okay. If delta E is negative, so the total Q plus W is negative, okay, then that means we would put that number just like we did for delta H in the product side. Okay? So it means that energy is being released by a system. So the total, the final minus initial energy involved, the change is going to be negative. So it's exothermic. Okay, if the change is positive, okay, so this is just the reverse reaction here. Okay, the delta H is positive, or excuse me, delta E, okay, just like delta H. Then it goes over here in the reactant side. Okay, so starting to see some similarities of delta E and delta H. Okay, kind of use them the same. Okay. This is just a simple little exercise. So if 1,200 joules of heat are added to a system, okay, and the system does 800 joules of work. This is very common. So normally in industry and even with, we're looking at our thermodynamics and steam engines and whatnot, usually something's put into our system and then we want it to do what? Put out work, right? We want it to do some sort of useful work on the surroundings because that's usually what we're trying to go for, right? We want an efficient, production of something, of energy. Okay, so if we had 1,200 joules of heat added to a system, so that means 1,200 joules of heat is being put in to the system. So that's going to be a positive Q, right? Okay. But then the system, you put in 1,200 joules and the system puts out 800. So that means its Q is negative. Excuse me, its W is negative. So all in all, the total change is 1,200 minus 800 that was put out. And so we still have a positive delta E. Okay. Notice here, this is delta E for the system. Okay. What if we think about delta E for the surroundings? Okay. Think about it in the reverse. Okay. So that's this question. Think about what's happening to the surroundings. Okay, all you're going to need to do is flip your signs, right? Okay. Okay, we think about surroundings, the delta E now. Okay. The 1,200 joules of heat that's added to the system is being lost by what? The surroundings, right? So it's now, I don't remember if I have this under here. So that's our answer. We have negative Q. Okay, then the system does 800 joules of work on the surroundings, so now our W for the surroundings is positive. Okay, so we end up with negative 400 joules. So the surroundings still lost 400 joules of heat. Okay, so that's just simple exercise to see kind of what's going on. But we really want to relate this to, so in maybe physics, different class, you might keep going with different ways you can do work, force over distance. Okay, but for chemistry, we're concerned with chemicals, right, and with compounds and what they do. So here's dry ice, okay, CO2. Okay, so it's just the solid form of CO2. Anybody ever touched dry ice before? Okay, I hope you probably didn't touch it for very long. Okay, so it hurts if you usually need to wear gloves or something on your hands. It's very, very cold. All right, when you put it into this Ziploc bag here and we close it, seal it up, okay, it's going to absorb heat from the surroundings, right? Okay, so it's going to have a positive Q, and this is what is very common, is to have a positive Q, so to put in some heat and get out work, right? That's what we said earlier. So then it starts forming gaseous CO2, okay, which builds up pressure, correct? When we have a gas, what does it do? It expands to fill the container, and it evolves pressure. So if we look here, if we put a book on top, so isn't that work? You start out with it, just flat with the CO2 solid. It works. It pushed the book over some amount of distance, right? Okay, so this would be an example of work done by a chemical reaction or by a chemical. And usually in chemistry, really the only type of work that we have, because we're not trying, chemicals aren't, we don't do a reaction for it to knock things over. That's not the idea. Okay, so usually pressure, the buildup of pressure is really our only form of work done by a system. That's kind of what we're looking at, especially in the lab anyways, in our kind of setting. Okay, so we're looking for, so here you have a positive Q. It absorbs heat from the room that it's in, and it releases work. Okay, so here's the final kind of, I know we're about to be out of time here, but here's the main idea. This is how delta H and delta E are related. Okay, they're related by pressure and change in volume. Okay, so delta H is our enthalpy, delta E is the internal energy, okay, and P, change of V, is the work done by a system. Okay, usually, like I said, pressure is the only type of work that a chemical can do, and so when it does have pressure, the volume increases, right? It changes, okay? But for most, okay, so for most of our reactions, we don't really want an expansion or a buildup of pressure or a change in volume, okay? So for most of our chemical reactions, we confine them into some sort of round bottom flask, some kind of smaller container where we get very little, if any, change in pressure and volume, okay? So if you don't get change in pressure and volume, that was our only difference, right? This was delta H, okay, or maybe it was backwards there, forget which one, it was delta, okay. So if we essentially get no volume change, no pressure change, then delta H is equal to delta E. Okay, and so the last slide here to look at is the change in enthalpy, and typically our delta H, it states that the reaction is at constant pressure, right? We've been talking about being at constant pressure, okay? And our delta E is supposed to be at constant volume, so more than likely your chemical reaction, you're not going to get much change, if any, here. So the only difference between delta E and delta H, as far as we're concerned in chemical reaction, is the P and delta V. Okay? But unless I tell you otherwise, that there's a change in volume or pressure, then you know that delta H equals delta E. Okay? So that's the roundabout way. You guys look like you're so ready to get out of here, but believe me, I spared you like a whole nother lecture by just telling you this and this. So I had to listen to it for 3 lectures, so you can get over it. Just kidding. Okay. I'll see you in lab at 1 o'clock. Be sure you wear long pants, closed-toed shoes, no shorts. So, until with a smiling face. I was just kidding. Everybody was. I know it's somewhat boring.
That's a very southern female thing to do.
What?
Smiley face tell all.
Oh. I gotcha.
You did?
Yep.
Awesome.
Yeah, I really did. I was trying to, when I was doing this lecture a while back, I was like, there's got to be an easier way to not listen to this for 3 lectures.
I was just
So.
thinking about what it must look like from where you're standing. It must look
Oh
like
yeah, when it gets close to time, I know, because everybody's fidgety and, yes. Yes.
I had Mr. Cox last
Yep.
one, and you said something about a safety video we have to watch for lab.
Yeah.
But I don't remember ever watching one for that, so I think I might need to watch it again. 'Cause
Okay.